8 athletes are lined up at the start of a race. Only 3 medals will be awarded: gold, silver, and bronze. In how many different ways can these medals be awarded? This is a permutation problem because the order in which the medals are given matters. Gold is not the same as silver, and silver is not the same as bronze. Let's solve it 2 ways. First, using the box method, then using the permutation formula. We'll start with the box method. We have 3 medals to give out, so we draw 3 boxes. First box. How many choices for the gold medal? There are 8 athletes, so that's 8 options. Second box. 1 athlete has already won gold. That means 7 athletes are battling for silver. Third box. 2 athletes already got medals, so only 6 athletes are left for bronze. Now multiply. 8 times 7 times 6 equals 336. So there are 336 different ways to award the 3 medals. Now let's confirm with the permutation formula. We're choosing 3 athletes from 8, and order matters, so we use the permutation formula. We substitute 8 for the total number of athletes n, while the value of r is 3, since we are selecting 3 athletes to share the 3 medals. So we get 8 factorial, which is 40,320, divide by 5 factorial, which is 120. This gives us the same answer, 336 different ways. 12 friends are attending a dinner party. The host wants to seat them at 3 separate tables, with exactly 4 persons at each table. In how many ways can the guests be assigned to the tables? We're grouping 12 persons into 3 groups of 4, but here's the catch. The order within each table doesn't matter, and the tables themselves are identical. That is, unlabeled, based on the context. This makes it a combinations problem, which again can be done using the box method or the combinations formula. We'll use the formula. Let's choose the first group of 4 persons. That's 12, choose 4. From the remaining 8, choose the second group of 4. From the final group of 4, we choose all 4 to be seated at the third table. So, to get the total number of arrangements so far, we can use our calculator. 12 choose 4 is 495, 8 choose 4 is 70, and 4 choose 4 is 1. So we get 34,650. Now, if the tables were numbered and different, our solution would 34,650. But since the tables are identical, swapping groups between tables doesn't create a new arrangement. There are 3 factorial or 6 ways to rearrange those 3 identical tables, all of which are included in the 34,650. So we must divide by 6 to correct the overcounting. So the final number of ways, the 12 guests can be assigned to 3 identical tables, with 4 guests each, is 34,650 divided by 6, which is equal to 5,775 ways. Always remember, when dividing people into identical groups, you need to account for duplicate arrangements by dividing appropriately. That's by the factorial of the number of persons or objects in each group. Let's solve another tricky permutation problem. How many 4-digit numbers less than 5,000 can be formed such that the number is odd? First, we know we're forming 4-digit numbers. That means the first digit cannot be 0, since 0 would make it a 3-digit number. Also, the number must be less than 5,000. That tells us the first digit has to be less than 5, so the choices for the first digit are 1, 2, 3, or 4. 4, that's 4 options. We're also told that the number has to be odd, so the last digit, that's the units digit, must be one of the odd digits, 1, 3, 5, 7, or 9. That gives us 5 choices for the last digit. The second and third digits can be any digit from 0 to 9, so that's 10 choices each. Therefore, the total number of 4-digit numbers less than 5,000 that are odd is 4 times 10 times 10 times 5. So our final answer is 2,000 such numbers can be formed. Let's tackle a popular combinations problem involving a group selection with a condition. A group consists of 7 boys and 9 girls. A 5-member committee is to be formed, and it should have at least 2 boys. How many different ways can this committee be formed? Let's start by understanding what at least 2 boys really means. It means the committee must have 2 or more boys. So let's consider all valid combinations of boys and girls that add up to 5 members. So we can have 2 boys and 3 girls, or 3 boys and 2 girls, or 4 boys and 1 girl, or 5 boys and 0 girls. We'll calculate the number of ways to choose each combination, and then we'll add them all up. We are choosing 2 boys from 7, so 7 choose 2, and we are choosing 3 girls from 9, so 9 choose 3. So this case gives 21 times 84 equals 1,764. Next, we are choosing 3 boys from 7, so 7 choose 3, and 2 girls from 9, so 9 choose 2. So this case gives 35 times 36 equals 1,260. Next, we are choosing 4 boys from 7, so 7 choose 4, and we are choosing 1 girl from 9, so 9 choose 1. So this case gives 35 times 9 equals 315, or finally, we are choosing 5 boys from 7, so 7 choose 5, and 0 girls from 9, so 9 choose 0. So this case gives 21 times 1 equals 21. Now, let's add all the valid combinations. 1,764, 1,260 plus 315 plus 21 equals 3,360. So, the number of ways to form a 5-member committee with at least 2 boys is 3,360. And that's our final answer. Let's solve a classic and elegant math problem that's often called the handshake problem. At a dinner party with 20 people, if each person shakes hands with every other person exactly once, how many handshakes take place? Here's how we think it through. Every time 2 people shake hands, that's 1 handshake. So we're not counting how many handshakes each person makes. We're counting the unique pairs of people who shake hands. So the real question becomes, how many ways can we choose 2 people from a group of 20? That's a combination problem. So in this case, it's 20 choose 2. Using a calculator, 20 choose 2 is equal to 190. That means 190 unique handshakes take place at the dinner party. How many unique 3-letter words, real or not, can be formed from the letters in the word blessed? First, let's look at the letters in blessed. The word has 7 letters, B, L, E, S, S, E, D. But we have some repeated letters here. The letter S appears twice, and the letter E also appears twice. So here are the unique letters, B, L, E, S, D. But we have to account for repetition when calculating the number of unique 3-letter arrangements. Let's break this into cases. The first scenario is the case where all 3 letters are different. This means we'll have to select the 3 letters from the set with 5 unique letters. This is a permutation problem since the order matters. This is because each change in arrangement is a different word. So the number of ways to select 3 letters from 5 is 5p3. Using our calculator, that's 60. The other scenario is the case where two letters are the same and one is different. This can only happen if the repeated letter is E or S, since those are the only ones that occur more than once. Let's first look at the possibility where we get two E's and one different letter. The other letter to complete the three-letter word would be from the set B, L, S, D. That's 4 options. Now, any of the letter selected from the 4 can be placed in any of 3 slots by moving around the 2 E's. So this gives 4 times 3 equals 12. 3-letter words with 2 E's can be formed. The exact same logic can be used for the number of words that can be formed with 2 S's. Choose one letter from B, L, E, D, 4 options, and each gives 3 arrangements. So again, 4 times 3 equals 12. So total for case 2, 12 plus 12 equals 24. So we add up the cases to get our final answer. 60 plus 24 equals 84 unique 3-letter words can be formed from the letters in B, L, E, S, S, E, D. In the next video, we'll look at circular permutations. Give us a thumbs up if you enjoy these videos. Don't forget to comment, share, and subscribe. See you soon.